Let's do some more examples with the Simplex method on standard maximization problems. So the first thing we want to check is to make sure we actually do have a standard maximization problem. The objective function is maximized, all variables in the problem are non-negative, and each constraint can be rewritten so that the expression containing the variables is less than or equal to a non-negative constant. So here's an example here. We're going to put this problem, this linear programming problem, into an initial simplex tableau. So first question, is it a standard maximization problem? Let's check. Okay, the first thing says the objective function is supposed to be maximized. Yep, says so right there. Then it says that all variables in the problem are non-negative. And here all variables are non-negative. What does that look like? Remember, we classified numbers 3 ways according to sign: positive, 0, and negative. So if something is non-negative, it's not negative. That means it's the other two options, 0 or positive. Okay, so if all variables are non-negative, that actually looks like this. That's this piece right here. Because x, you see here, can be 0 or it can be positive, and y can be 0 or it can be positive. So the variables are non-negative. So the objective function maximized is from right here. And then the third criteria was that each constraint could be written so that we had variable stuff, very technical term, variable stuff less than or equal to a non-negative constant. Right here. Variables are less than or equal to a non-negative constant. So now we're looking, this one we're looking here. So do you see we have stuff with expressions with the variables on the left, less than or equal to sign, and then a number over here that's not negative, 0 or positive. So that is also satisfied. So yes, this is a standard maximization problem. We are good to go. We can use the simplex method. So to use the simplex method, we're going to change the form of this. We're going to take this system of inequalities and we're going to rewrite it in such a way so we can put it into a matrix. Our matrix is going to be our initial simplex tableau, but it's going to be a matrix. So what we're going to do is look at each piece individually. This down here, the variables are non-negative, is not going to go in our simplex table. But the constraints will go, and so will the objective function. So we're going to introduce slack variables. We're going to get 1 for every constraint. Slack variables pick up the slack. They help us change an inequality to an equality. So we have x plus y plus s1 equals 4. We are replacing this less than or equal to sign with plus s1 equals. Think about it like this. If x is 1 and y is 2, 1 plus 2, x plus y is less than or equal to 4. That's a true statement. But if we want to make this inequality an equal sign, you'd have 1 plus 2, that's 3, plus 1 would equal 4. You're replacing that inequality with a slack variable and an equal sign. Remember, x can be 0 or positive, so if x is 0, and even if y is 0, we'd get 0 plus 0 is less than or equal to 4. We could rewrite less than or equal to 4 as 0 plus 4 equals 4. We're replacing that inequality with plus some number equals. There are infinitely many choices for x and y. I just pulled a few out of the air. So no matter, depending what I pick, that's going to change the value I have to plug in here to pick up the slack. It's going to vary, thus it's a slack variable. So every constraint gets a slack variable. So 2x plus y less than or equal to 5. We're going to rewrite that less than or equal to as plus a new slack variable equals. So 2x plus y plus another slack variable. It has to be different than S1. It could be a different value equals 5. So we're replacing that less than or equal to with plus a slack variable equals. So those are the constraints. Now they're equations, right? Equations go into matrices very nicely. Now we're going to take that objective function. It's going to go at the bottom. The objective function, we're going to rewrite so that all the variables in P are on the same side of the equation, and the coefficient of P is 1. So if you go back to your form here, we created slack variables. We're going to rewrite the objective function so that the coefficient of P is 1, and all variables in P is also a variable, but all the other variables in P are on the same side of the equal sign. But the coefficient of P has to be 1. You see right here, the coefficient of P is already 1. Okay, that just means we have to move these variables over here. So then we have P equals 3x plus 4y. So we're going to take these and move them over, which means we're subtracting 3x minus 3x. We're subtracting 4y minus 4y. So negative 3x minus 4y plus P equals 0. And that's going to go at the bottom. So notice we are going to have some new variables. We had x and y's and p's up here. We're going to have S1 and S2 as well. So we have an x column, a y column, an S1 column, an S2 column, a p column, and then we're going to have our constant column. This is just a matrix. It's going to be treated just like a matrix. So we're going to call it something fancy, the initial simplex tableau, but it's just treated like a matrix. Sometimes you'll see there's a line drawn right here, so it's going to let me look a little different, but it's going to be a matrix. So the constraint stuff is going to go in the top. So we rewrote the constraints, the inequalities, as equations. So we get 1, 1, taking the coefficients of these, 1x plus 1y, plus 1s1, so we're going to get a 1 right here. Notice there are no more variables here, right? So there's no s2 and there's no p. So we get 0, 0. Our constant is 4. And then we do the next one. 2x plus y plus s2 equals 5. So 2 is coefficient of x. Coefficient of y is 1. Notice there is no s1, so I put a 0 there. S2 has a coefficient of 1, and P has a coefficient of 0 because I don't have 1, and the constant is 5. Do you see that those are the constraints that we've tweaked and made them equations? Okay, the next thing we do is we draw a line right here to separate the constraints from the objective function. And then we're going to put this objective function that we've rewritten down at the bottom. So the objective function is negative 3, because it's an equation, I'm putting the coefficients in here. Right, this is the x column, so negative 3 is a coefficient of x. Then put a negative 4 in the y column because it's negative 4y. There's no s1 given, so I put a 0 there. No s2, so I put a 0 there. There is a p, the coefficient of p is 1, so that gets a 1. And the constant is 0. So the objective function goes down here. Okay? So one thing you're going to notice is that if you look at your slack variables and your P, you're going to get an identity matrix, the piece that we would have if we had an identity matrix. Sometimes you're going to see this with brackets, but you don't have to have brackets. Just sort of depends on the style. Some books have it, some books don't, but this is a matrix. Let's try another one. Same directions. Put this into an initial simplex tableau. So we're going to introduce a slack variable for every constraint other than these guys. Let's make sure it's a standard maximization problem. Is the objective function maximized? Yep. Are the variables non-negative? Yep. For the constraints that we're actually going to use, do we have an expression with variables less than or equal to a non-negative number? Yep. Okay, so each one of these constraints gets a slack variable. So we're replacing this inequality with plus s1 equals. So we get 2x plus 4y plus 3z plus s1 equals 14. we're going to replace this inequality with a new slack variable, a different one. So we get 2x minus y plus 5z plus s2 equals 50. And this guy down here, this inequality, turns into plus s3 equals. So we have 4x plus 9y plus 11z plus s3 equals 81. And remember, the objective function goes at the bottom. Move all of the variables on the same side as p. So negative 8x minus 3y minus 4z plus p equals 0. And then we look at all of the variables that we have. We have x, y, and z. We also have an S1, an S2, an S3, and a p. So let's make a column for each, an x column, a y column, a z column, an S1, S2, S3 columns, a p column, and constant. I'll draw a line right here. Like typically you'll draw a line right here too. And then we just put our equations, and these are equations now. They go very nicely into a matrix, a row at a time, right? 2, 4, 3, right? So 2, 4, 3. Be careful with the slack variables. We have an S1, so this guy gets a 1. We do not have any more slack variables, and we do not have a p, so we put zeros there. Constant is 14. Does that make sense? Let's do the next equation. 2x minus y plus 5z. So 2, negative 1 plus 5. That's the x, y, z part. Now, S1 is the next variable that's listed. There is no S1 here, so I put 0 as a placeholder. There is an S2. The coefficient of S2 is 1. There's not an S3, and there's not a p, but the constant is 50. And now we're on this equation. So 4x, so we put a 4. 9y, put a 9, plus 11z, we get an 11. There's not an S1. There's not an S2. We do have an S3. Coefficient is 1. There's not a p. Constant is 81. And if you notice, those are the equations that came from our constraints. So we put those at the top. Now we worry about the objective function. We put that last. So the objective function is this one right here. So negative 8, negative 3, negative 4. There's no S1, no S2, no S3. Coefficient of p is 1. And here's a 0. Isn't that fun?